Testing. Testing. Can someone hear me?
Yes, doctor.
Yes.
Yes, doctor.
Yes, doctor.
Right. Okay. Okay, are you ready for the class?
Yes, doctor.
Yes, doctor.
Okay, let's begin. So, Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala ashraf anbiya wal mursalin wa ala alihi wa sahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul idza syi'ta sahla. Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Is this your first class for today?
No, doctor.
Yes.
First class?
Oh, doctor, second class.
Right. Okay, so let's proceed to the lecture 2, which is particles equilibrium in 2D equilibrium. So what you will learn for today, we do have 4 or 5. The first one, you will learn about the equilibrium condition in 2D for particle. Okay, and then you will learn on how to develop a free body diagram for 2D particle. Free body diagram is very important. So if you are not well good in FBD, then this will be disaster. So basically, you have to know FBD. You have to know on how to draw FBD. Okay, it is not only for static. It is for the solid mechanic later on as well. Okay, solid mechanic in year 3. So make sure that you are familiar with FBD. So number 3, you will learn on analysis approach. We do have 3 different methods: graphical, trigonometry, and rectangular method. Okay, typo there. Okay, number 4, you will learn about the cable, the system itself. Okay, we have many systems. We have cable, rope, wire, and pulley. We do have a truss. Okay, we do have reaction and so on. Okay, in this lecture, you will learn only on the cable, wires, or pulley. Okay, and of course, we do have question and answer later on. Okay, so I believe that Dr. Aisha already covered this one. It is about equilibrium of a particle in 2D, 2 dimension. So basically, we do have 2 axes in 2D, x and y axis. So in this lecture, we can know that equilibrium system can be equal to 0. So meaning that a particle is in equilibrium when the resultant of all forces acting on it equal to 0. So either x or y, it should be equal to 0. Okay, so this one is the resultant. Okay, must be equal to 0. So okay, before I proceed further, can you state which Newton's law belongs to this equilibrium? Sorry, I cannot hear you.
Newton first law.
First,
Newton first law.
First law.
second, third.
First. Law of
First.
inertia.
Third law, Daniel, not third law lah. The answer is first, second, third.
First.
Yes, the answer is first Newton's law. So any particles, if having constant velocity will be remain zero. The acceleration will be remain zero. So you have to remember like equation for the first Newton's law, F equal to 0 actually. Okay, second Newton's law, F equal to ma. Okay, so the third one is about reaction and action. Okay, so
F equal to negative F.
sorry,
F equal to negative F.
which one?
Third law.
Third. Yes, correct. Reaction and action as well. Okay, so let me erase this one. Okay, so equilibrium system is belong to first Newton's law. Okay, first Newton's law. So all axes, all resultant must be equal to 0. Okay, all forces. In this case, we can say forces. Maybe in the future you will learn about moment. So moment, if in the equilibrium system, moment should be equal to 0 as well. Okay. So free body diagram, FBD. So you have to get familiar. You have to expert on how to draw FBD. Otherwise, if you wrongly draw the FBD, your answer will be wrong as well. Okay. So make sure that you good in FBD. All right. So on how to draw FBD, you have to identify the first one. Identify all relevant forces. Okay, we do have external, internal forces of the particle. Okay, so the procedure, you can see these steps, this procedure on how to draw. The first thing is that you have to draw the boundary of the chosen section. Okay, so let's say, for example, I give you example here. Let's say you have two different rigid body like this. Okay, and I state the first one is A, the second one is B. Okay, and maybe we do have P here. Okay, and it's a cable, for example, and then this is maybe a wall. Okay, all right. So the meaning of draw the boundary of chosen section, meaning that you have to choose either one. Let's say the question, the problem asking you to draw A. So you have to draw a particle for A. So FBD for A should be like this. Okay. Dot. Okay. Dot first. You have to draw boundary. Boundary meaning for the particle lah. Boundary of the particle. This A. This A. Okay. This A. And then the second input, the second sentence, input all external forces acting on the particle. So from A here, you can see the external force, which is P. Okay, you have to put P here. P. All right, this is done. The number 3, for a particle with mass, let's say this one got mass 1 lah. Sorry, mass 2. Okay, so for the particle with mass, let's say this object of A got m1 mass. Okay, so you have to put weight. Okay, put weight here. All right, and must be acting at the center of gravity of the particle in vertically downwards direction. Okay, should be vertically downwards. Okay, and the last one, for a particle touching a surface, there is normal force. Okay, normal force. So let's say this one on the surface lah. Okay, so we do have a normal force acting on the particle as well, like this. Okay, so this is your FB, the simple example that I can give to you. Okay, all right. Any questions so far?
No, doctor.
We solve the tutorial free body diagram.
I think I cannot hear you lah. What did you say just now?
We solved the tutorial on free body diagram. Any questions?
The question.
We solved the tutorial
You already solved the tutorial.
on a free body diagram. Yes. Any questions?
Oh,
Free
okay.
body
A free
diagram.
question. So I can skip this one.
For me, it's okay. I don't know about the others.
All right. Okay. Let me read the chat. Chat, eh? Mana chat ni? Mana chat? Someone said normal force are only on the. Okay, Asan asking me normal forces are only on for the object at rest or all subject. What do you mean by all subject? All subject or all object? So no matter how the object is at rest or moving, it should be having normal forces. Okay, in dynamic later on you will learn, even though the object is moving, the normal force is there as well. Okay, in dynamic later on you will learn it. Okay, good question actually. All right, I will go fast. I will go quickly because you have learned this with Dr. Aisha. So this is another example. Okay, this is another example with one single rigid body M with mass. Okay, you have to draw FBD like this. So, okay, you have to draw FBD of particle. So this object will represent as particle like this. Okay, and then you have to put external forces of P. Okay, external forces of T. Okay, and then this is the internal force. Okay, internal force and internal force. Okay, all right, that's it. Easy, right? Easy. Okay, solution procedure. 3 methods for solution. We do have graphical, trigonometry, rectangle components. Okay. So basically graphical we're not using in our syllabus because you have to have a ruler and protractor. Okay, and then it very tedious work. So you have to draw manually in a sheet of paper, and then you have to assume 1 cm to equivalent to 50 Newton, for example, and then you have to use protractor and so on. So that one is very tedious. That one can be done if you have many times. Okay, all right. Okay, so we will go straight away, okay, to trigonometry and rectangular, and then I will show you on how to use that method. Okay, for this problem, okay, if you can see at the screen right now, this is the simple system that you have to solve. Okay, you have to find the tension cables AB, this one, okay, this one, and this one BC, okay, using equilibrium system. Okay, so the first thing is you have to draw FBD as shown in here. Okay, a particle with the external forces TBA, TBC, and also the internal force, the weak, okay, with angle. Okay. Okay, a little bit about graphical method. As I mentioned, you have to use a ruler and protractor. Okay, you can use a suitable scale. It depends on you. Let's say you want to set 1 cm equal to 50 Newton or 1 cm equal to 100 Newton. Okay, so you have to use that. Start with a known magnitude. Construct a line to represent a line of action. The other line of action must pass through the above line and end at the start point. You start here, and then you must end the line here as well. Okay, so using ruler, okay, once you have this one, this line TBC, this line TBA, and this line you will get the value of TBA and TBC. Okay. Okay, just ignore, not ignore, but this is the basic thing that we use for the graphical method. But normally we're not using this method in our calculation. So you will use either trigonometry or rectangular component. As I said last section, last class, trigonometry not suitable for all problem. Okay, if the forces more than 5, then trigonometry is not suitable. You have to use a rectangular component. Okay, so trigonometry having lacking as well, and the best method that I normally use is rectangular method. So never mind, it's up to you. If you want to use trigonometry, you can proceed with that. Okay, so if you are using trigonometry, you have to put the FVD into a triangle shape like this. Okay, you have to put the angle 20 here, 70 here, the initial angle of TBA 40, okay. All right, you will get the angle of 50 using mathematics. Okay, I will not go further on this method. Okay, I believe that you are already familiar with the mathematics solution. So I will go to the rectangular component. Okay, for the rectangular component, every single force, you have to resolve it. Okay, you have to resolve the forces into X and Y direction. Okay, into X and Y direction. So we have TBC, okay, having the angle there, and then you have to resolve in TBCX, for example, okay, and TBCY, okay. So you have to resolve in X and Y direction. Similar goes to TBA, TBAY, TBA, oops, TBAX, okay. All right, and you have to use this formula first, Newton's law, okay, to get the first equation. All right, so later for the y component, using the first Newton law as well, okay, and you will get the second equation. Okay, then you substitute the first equation, this equation, into the second equation, this one. Okay, this one. Then finally you will get the answer for TBA first. Okay, and then substitute this value into this one, you will get TBC. All right, easy, right? So if you're not okay, what I can say is that you have to go to exercise, then we can know it's easy or difficult. Okay, exercise will be in the end, at the end. Okay, go to cables and ropes and wires and pulley. Okay, before I proceed, any question about the FBD? Any question?
No, doctor.
No. Can I proceed or end the class?
Proceed, doctor.
Proceed. So we will proceed until 1 p.m. Is it okay for you? Correct.
Why 1 p.m., doctor?
Yes,
Doctor, I can't.
I
I
want.
can't, doctor.
I think should be 11.
Should be 11. Okay. I just want to receive response lah. Kan, tak nak lah short sendiri cakap seorang-seorang. Alright. So, okay, let's me proceed. Okay, cable, ropes, wires, and pulley. Okay, so the first one, the first sentence there. And in this syllabus, we assume the cable or ropes or wire to be inextensible. Okay, to be inextensible. Okay, so in real situation, you know that the cable can be extended, like this rubber lah, rubber. You can extend this rubber like this. You can extend this rubber like this. But in static, we assume it not extensible. Okay. So you cannot extend. This is the original. You cannot extend. Okay, you cannot extend like this. Okay, when we have P, we only assume the blue color. Whenever we have the pressure, the rope, the wire will not extend. Okay, and the second one, forces acting on cable are in tension. Yes, of course, forces acting at this point, for example, will be tension T. Okay, will be T, always tension. When a cable pass a pulley, the tension is same. Okay, so we do have a pulley system like this. Okay. Oops, sorry. So we do have a cable like this, for example. We have cable like this. And then if you draw FBD of the pulley, you will get, let's say this one is E. You will get this FBD. Okay. The tension is same. 2T, for example, this T and this T. Okay, the tension, the magnitude of T will be similar, will be same. Okay, and last, the second last, pulley Asimov, no friction.
So the tension should be up, right? Or down?
Sorry?
The tension should be up.
Yeah. No, it should be tension out from the point.
So the down is the weight.
This one is cable. No, wait. This is not an object. So never mind, I will show you later on. Okay.
Okay.
Okay, pulley Asimov. Okay, pulley Asimov, no friction. Okay, in real situation, of course, in this interface, we do have friction. Okay, friction because we have two different body. Okay, the cable and also the surface of pulley. So in our static case, we assume there is no friction, and also the dimension of pulley are neglected. Okay, so all right. Example of a cable, ropes, wires, and pulley system. If you can see here, one wire attached to the, let's say this is the shilling. Okay, going through to the pulley system, and the wire end here. Okay, so from here you have to draw FBD. Okay, let's see. You want to find the T value here or P value. Okay, pressure, and then the FBD will be like this. Okay, so FBD at point A with a particle size. Okay, you have weight here, you have 2T. Okay, 2T, because there is two direction that acting on the A point A. So that's why we have 2T and 1 weight. Okay.
Okay, doctor.
Okay, the second example, you have two different pulley. Okay, you have two different pulley, and then this one is same like before. Okay, same like before. You have this system, this wire along the way. Okay, so if you want to draw FBD at point A, you have to consider this region only. Okay, that's why in the example we have this FBD. Okay, this FBD. All right, let's say we do have, I introduce one more point, which is B. Okay, can you state to me, can you show to me maybe the FBD of point B?
2t to downward.
All right, is it correct? Oops. Is it correct? Hmm? Any argument from others?
I think yes, Doctor.
Which one yes? Yes correct or yes wrong?
Correct, Doctor.
No, the answer is wrong.
Okay, Doctor.
Is it T?
Can you say to me what is the thing that we miss?
Upper force, Doctor.
No, MG, there is no object attached on the rope for the system at B.
Upper force, Doctor.
Upper force, which force?
At point B.
Yalah, which force? What force?
T tu, Doctor.
Ah, tak dengar.
Normal
Besi,
force.
Doctor. Besi. Normal force, Doctor.
Normal force.
Sorry?
Normal force.
Almost correct. But we cannot say no.
Upwards.
Yes, but yes, the answer yes, upward. There is one force because you are not learning. Second one, what do you mean? Second one?
Oh, so doctor, one tension upward and one tension downward.
No, this one is correct. This one is correct. Okay, let me explain. Because you are not learning reaction and action. Okay, you are not learning. Yeah. At the moment, you are learning the first Newton's law. Okay, so in later lecture, you will learn action and reaction. Okay, action and reaction. Based on this one, you will have additional reaction here. Okay. All right, this one will be covered in next class. Okay, so that's why in this example we only show this FBD. Okay, to avoid confusing. Okay, if you have FBD about point B, then you have this one. The R is coming from this beam lah, because it attached to the shielding, for example.
So the reaction is to balance the 2t because it's in equilibrium.
Yes, correct.
Okay.
Yes, that's why we do have our reaction to balance the system. Okay, next one. Third example. Okay, maybe this one is not really difficult. Okay, because you have to consider this region. Okay, you have to draw FBD. I believe that Dr. Aisha also shown this one. Okay, if yes, then can you say to me how many T there? No.
3t upward.
Oh, Dr. Aisha didn't show this one.
No, Doctor.
Okay, never mind. So my question is, how many T there? How many tension?
3, Doctor.
3T.
3.
Yes, correct. So the 3T should be pointing?
Upward.
Yes, correct. So the T should be pointing outward. Why similar T? Because this wire is attached together like this. It is continuously. okay, is not attached to other body, or maybe there is no other cable in this system. There is one cable in this system only. So that's why we have the similar T value. Okay, so you will get the FBD like this. Okay, 3T upwards and MG downwards. Okay, so I extend my question to you. If I introduce another point, which is point B, for example, this B, okay, let's say B here. Okay, so can you say to me,
2T
how many-
downward and 1 reaction upward.
okay, great. So the answer is correct. 2T downward reaction. Okay, so this one reaction will be covered later on, as I said. Okay, that's why we only show you this one. Okay, this one. So how about how about C? If I introduce C point here, this C.
T downward, one reaction. Three T downward, Doctor.
T downward.
Doctor,
Yeah. Yes.
3T downward with the force of gravity, reaction upward.
No. Okay, never mind.
2T upward, 1T downward with force of gravity.
No. Okay,
MG
never
downward.
mind, never mind. You can try. Later I will explain. Is there any idea?
T downwards.
No.
MG
Plus.
downward. Reaction
Sorry?
upward.
Sorry, how
Doctor,
much?
2T downward, 1 reaction upward.
2T downward, 1 reaction upward. Okay, almost. Good. Okay, the answer is like this. Okay, the answer is like this. Reaction upward. Okay, we do have this one, this line. Okay, T, and this T with angle. Okay, and don't forget we do have this one as well, reaction as well. So I can say that this is reaction 2, another one is reaction, should be a straight line at reaction 1. Okay, this is the FBD for point C. Okay, so just introduce you early about the reaction and action. Later on, you will learn further about reaction and action, which is third Newton's law. Okay, this one. So at point B, how many forces for the FBD?
MG downward and 3 tension force upward.
Osam, I think your speaker, your mic is blurring. Not blurring. I cannot hear you.
Doctor, 2T in the diagonal like this, and 1P and FG downward.
Yeah, correct. So this one, 2P with a beta angle, 1P with a theta angle, and the last one is weak. Okay. All right. For another example, how many pressure, how many forces? Anyone?
reaction upward, and 2t
2t. Yes, correct. 2p. Okay. All right. My other question, why suddenly we put 2p? Why the previous example we put t? Yeah. Why this one we put 2t? Why this one t as well? In this case, we put, for this case, we put p. Why?
Yeah, external forces.
Because it's a pulley.
Because it's Pauli. When
Because it's mentioned from before.
can we put 2t like this as well?
Yes, no problem. It's only variables.
Yes, the answer no problem at all.
The same, doctor.
As long as the value is same, you can put any p, a, b, c, d, e, f, g as you like. Okay, but in this case, the system already put p. Then you have to put p lah. Okay, so the previous case, there is no p, t, a, b, c, d there. So you can put t. If the system already put the value, for example, you have to consider, you have to use the value. Okay, this one is more tricky. Okay, not very difficult, but a tricky one. Okay, so can you say to me the FBD for point B? How much forces there? Point B.
B plus T mg down, doctor.
Okay, good. The answer is correct.
B plus C.
Plus T in T mg. So because this system have two different cable. This is the first cable. Okay, we donate ST, for example. Okay, and the second cable is this one, from this point to this point, P. Okay, that's why we have P and T here. Okay, why we cannot put 2P? Because maybe P and T is not in same value, so you have to put P plus T. Okay, and then of course this one T lah. All right.
Yes, doctor.
Okay, I extend my question. How about point E?
P downward, T to the right, and reaction upward.
Okay, you miss one force. Anyone else?
Yeah. Sorry, P plus T and P downward reaction.
Yes, correct. So this one should be similar like this. Okay, P plus T, and then P downward, and then reaction. Okay. Okay, this is basic free body diagram. So you have to get familiar with the FBD. All right. So let's do this exercise. Have you done this one?
Doctor.
Huh? Tak dengar lah. No ke yes?
No,
yet,
doctor. Not yet.
Okay, if not yet, let's do together. You have to prepare sheet of paper and pen lah, and also calculator. So can you do it now? Together and gather. You do it now. You have to find the cable AB, BC, and also the mass. Okay, can you get it in 5 minutes? 5 minutes only. Okay, 5 minutes only.